This is section 3.6, two-dimensional crystallographic point groups. In the last section, we define groups as a set of elements and an operation between the elements of the group with the requirement of closure, identity, inverse, and the associative law. We also looked at symmetry operations, for example, mirrors and rotations, and we developed matrices in order to describe these operations. And finally, we proved that magnificent theorem, which says that only 1, 2, 3, 4, and 6 rotations are possible in a lattice. Why study point groups? Many physical properties of crystals are associated with their point groups. For example, pyroelectricity, piezoelectricity, ferroelectricity, external morphology or shape of the crystal, optical activity, etch figures, and indices of refraction. We will look into some of these properties later in the chapter. First, let's look at the external morphology of a crystal. The external morphology means shape, and phology means study. So here's the study of the crystal of caffeine, and you can see the molecule of caffeine is oriented within the crystal. Point groups also describe symmetries of molecules and the symmetries of orbitals forming covalent bonds. Here's a definition. A point group is a group of symmetry operations that leave at least one point of an object or pattern unmoved. An invariant point is a point that does not move under a symmetry operation. The identity holds all points invariant. The mirror holds all the points along the mirror plane invariant. And finally, the rotations 2, 3, 4, and 6, those are the crystallographic rotations, hold only one point invariant. The non-crystallographic rotations also hold only one point invariant. Translations will be excluded from point groups. The crystallographic point groups are point groups consistent with lattices. The rotations in these point groups are limited to the crystallographic rotations of 1, 2, 3, 4, and 6-fold. The number of crystallographic point groups is finite. In 2 dimensions, we have 10 point groups, and in 3 dimensions, we have 32 point groups. However, the other class of crystallographic point groups are the non-crystallographic point groups, in which no restrictions are placed on the point group. These are not compatible with the crystallographic point groups. There's an infinite number of non-crystallographic point groups. For example, n could be 19 or 72 or 5 or 8 in the figures below. And now we're going to examine the 10 point groups in detail, and we'll start out with point group 1. Point group 1 could be represented by this figure of a horse. There's no symmetry there. We also have an example of a molecule, which is the molecule of caffeine. Point group 1 is the identity point group, and it has just one element, 1. Since there's only one element, there's closure, and the associative law is trivial. The identity is 1, and the inverse of 1 is 1. Furthermore, the identity point group is a subgroup of every other point group. The order of a group is the number of elements contained in the group. The identity group 1 contains only one element, 1, and hence has order 1. Here's the multiplication table. 1 times 1 is 1. And here's the point stereographic projection and the symbol stereographic projection. For the point stereographic projection, we have the y-axis horizontal and the x-axis points downward. So and we divide our circle into 4 quadrants, not equal quadrants in this case, and the identity, for convenience, we place it in the positive quadrant, and we place it close to the x-axis, and there is just one element, and that's indicated by this red dot. If you take the determinant of this matrix, you'll see that it's positive, and thus there is no change of handedness when you operate the identity on a point, so the color will keep it as red. There isn't any symbol for the point group 1. Now let's move to point group 2. Point group 2 is the point group of the twofold, and you can see right here between the horse's hooves we have a twofold which takes the top horse down into this bottom horse. For the top horse, we can see the right front hoof is up, and if you look at the bottom horse, is that the right or the left? Yes, it's the right, so we have no change of handedness or footedness in this case, and so the determinant has to be +1. Here's an example of a molecule. We have 2 chlorine atoms, 2 carbons, and 2 hydrogens, and the twofolds right here, taking the this particular chlorine into the other chlorine here, etc. Point group 2, as we saw earlier in the last section, can be the twofold can be represented by this matrix: 1 bar 0 1 bar. If we multiply the two of them together, and we do that by multiplying the representative matrices, and we find out, we come right back to our old friend, the identity. So here is our multiplication table for point group 2. Point group 2 has order 2 because it has 2 elements, 1 and 2, and it has symmetry operation and 2 symmetry operations. It has a point stereographic projection. Again, we have the y-axis coming horizontal and the x-axis going downward. Here is the identity, and you have a twofold, and the twofold takes the identity and goes 180 degrees. And this is the matrix for the twofold. The determinant of that is 1, so there is no change of handedness, so the 2 dots are red. And here's the symbol for the twofold. Notice we have the use of the word 2. 2 refers to the point group, and it also refers to the operation. And of course we have it has order 2 also. Now we have referred to the proper operation. It has a matrix associated with the operation that has a determinant of +1. A proper operation retains the handedness of the object. All of the rotation operations are proper. Oh, here's our friendly giraffe. Our giraffe is going to help us with point group M. Here's a mirror plane going down through the giraffe. We can see the horns and the ears and the eyes, etc. Don't worry about his beautiful spotty hide. Here's an example of a mirror plane. So here's the mirror plane for our 2 horses, and the top horse is mirrored into the bottom horse, and here's the right foot is held up in the top horse, and this is the hoof that's held up. Which is it, right or left? That's right, it's left. I mean, that's correct, it's left. So we've had a change of handedness or footedness again here. And here's an example of urea, which is a molecule which has the carbon and the oxygen, the 2 nitrogens, and the hydrogens. Point group M, if we multiply the matrix for the mirrors, we come back to our old friendly identity. So we have our point group multiplication table. We have two elements, symmetry elements, 1 and m, and so the order is 2. And here is a picture of our horses. And now let's look at our point and symbol stereographic projections. Now, when we take I made these dots a little bit bigger. So we start out with the identity. We operate on the mirror. The mirror is right here along the y-axis, and we have a change of handedness, and it goes right up there. And here's the matrix, associated matrix. You take the derivative of that matrix, you're going to get -1 because you have a change of handedness. Now the symbol for the mirror is this heavy line. We color it purple because we always have an identity and the mirror image. So we're always going to have half of the operations in the point group with mirrors are going to be half red and half blue, so we can represent that in the purple mirror. An improper operation has a matrix with a determinant of -1, and it changes handedness of the object. The mirror operation is also called an improper operation. Now let's look at these two multiplication tables. The tables are identical if m and 2 are interchanged. Thus, we have a situation where we have the same multiplication table for two different groups. The two groups are 1 and 2. They have different elements, but they're isomorphic. So if two groups have the same multiplication table, then they are considered isomorphic groups. Isomorphic groups have the same order, but if you have two groups of the same order, it doesn't necessarily mean they're isomorphic. Now we're going to go on to point group 3. Here's a figure for point group 3. To get the figure on the right, I simply made those circles smaller. These are a series of large circles, made more of them, colored them blue, and you get a very different looking figure, but it's created with the same MATLAB program. Here we have a molecular example, which is a boron with 3 hydroxyls. The OHs are here, and you can see that you have a threefold. Point group 3, we've already gotten this matrix when we multiply 3 for 3 plus, so 3 plus times 3 plus will give me a new matrix, and that's going to be 3 minus. And here's our multiplication table. Note now we can distinguish for our symmetry operations and elements. They're both an element and an operation. So we have 1, 3 plus, and 3 minus for our operations, and the point group is 3. Now here is our point stereographic projection. Now we have the y-axis coming horizontal and the x-axis pointing downward. There's 120 degrees here, so if you run a threefold on this identity, you're going to get one here, exactly 120 degrees apart. This type of symmetry is indicated by a triangle, and here is the matrix. Now we can look at the matrix, the symmetry, and the multiplication table, and we can see here's the diagonal terms, and the off-diagonal terms correspond: 3 plus to 3 plus, 3 minus to 3 minus, 1 to 1. That means that the multiplication table is symmetric and that we have a commutative group. Definition: a commutative group has a symmetrical multiplication table. And the order in which the operation is performed doesn't really matter. For example, 3 plus times 3 minus is going to give me 1, which is this term here. 3 minus times 3 plus is also going to give me 1, and that occurs for every off-diagonal element, so therefore we have a commutative group. Let's move on to point group 4. We can, the matrix for 4 plus is 0 minus 1, 1, 0. 4 plus times 4 plus gives us an old friend back, which is 2. And if we multiply 4 by that 2, we're going to get a new friend, which is 4 minus. So here's our multiplication table. We have 4 elements. What is the order? Yes, 4. And it has the point stereographic projection. It's just what you'd think it would be. It's got the identity here, and then we put a fourfold on this identity, and we get 1, 2, 3, 4. And it's represented by a square, and the square has the angle side pointed up. And here is our generator matrix. Point group 2, actually, in red, is completely contained in point group 4, and thus is a subgroup of point group 4. This is what we mean by a subgroup. So here's a definition. A subgroup is a group wholly contained in a larger group. By this definition, the group itself is a subgroup of itself. However, a proper subgroup of a group has order less than the order of the group. So here we also see that we have point group 1. That's right here. And you always have point group 1 as a subgroup. And point group 1 is a subgroup of every other point group. And finally, point group 2 is a proper subgroup of point group 4. We can represent this by a series of vertical circles. At the top is the fourfold. As a subgroup of the fourfold is the top circle represents the point group 4. As a subgroup of point group 4, we have point group 2. As a subgroup of point group 2, we have point group 1, and we are connecting these lines. As you go up the ladder, so to speak, you get more and more symmetries. Okay, generators are a series of elements of a group such that every group element is obtained as a product of these generators. We can have one or more generators. 4 plus is the generator of point group 4 because all the elements of the group can be generated from 4 plus. Thus 4 plus squared is 2, 4 plus cubed is 4 minus, and 4 plus to the 4th power is 1, and we've generated all 4 of our elements. The international tables for crystallography, which we'll be using in chapter 4, lists 1, 2, and 4 plus as the generators for group 4. These are chosen to emphasize the subgroups. And I have created an appendix in the back, and the first part is the 2D point groups for each point group. I'll give the name of the point group, and then we have the symmetry operations and coordinates, and then we'll have a sequential number system assigned to that, 1, 2, 3, 4. And so the 1 can refer to either the operation or the coordinates. From the coordinates we can get the matrix. So the generators are the identity, 2, which just happens to be the twofold, and 3, which is 4 plus, or it could be this matrix. We've already gone over our point and symbol stereographic projections. The system is square, which we'll do in a few minutes. Now we have point group 6. Again, we have the matrix associated with point group 6. We have 6 operations, and here's an example. So you just make 6 spirals, and here are our point group stereographic projections. You have a, if you start out here for the identity, here is the y-axis, and here's the x-axis, and then we generate all of these from this. We go a 6-fold around here. We indicate that symbolically by the hexagon with the point upward, vertice upward, and we have, here's the associated matrix generator. The previous 6 point groups, 1, 2, 3, 4, 6, and M, are cyclic groups. A cyclic group needs only one element to generate the entire group. And we've just gone over how the one element 4 plus will generate all of the members of the group. For the next point groups, the mirror is combined with a rotation. Oh, here's our friendly giraffes. We're going to look at point group 2MM. Here's an illustration of it with 4 giraffes helping out. You can see there's a mirror plane here and a mirror plane here and a twofold right in the middle. So this giraffe two-folds into this one and this one two-folds into that one. You can tell the twofold by picking up your computer and rotating it around by 180 degrees, and you'll see the picture is the same. We have 2 matrices that will represent the point group 2MM, matrix for 2, which taken by itself would give point group 2, and matrix M or MY would give point group M. But if we take them and multiply them together, we get a group in itself. And here we have a new element being generated, which turns out to be MX. And here's our multiplication table. It has order 4, and it has 4 symmetry elements. And here's an example of pentacene, which has a twofold and 2 mirrors. And here we have the point stereographic projection. Again, this will tell us you have 4 elements. So here's our 4 elements. And you can see you start out with the identity. Here's the twofold. And here you have a mirror across. This one is a mirror across Y, so that's MY. And here's a mirror, and then here's the mirror across X. And the symbol for the stereographic projection is the 2 perpendicular mirrors with the twofold right in the middle, and you can see that's represented here on pentacene. I want to show you something interesting here. If we look at the symbol stereographic projection, and you have one mirror plane, and you put in the twofold, and you operate the twofold on that mirror plane, you get that same mirror plane back. However, we always generate in our multiplication table the second mirror plane, and that's why we have 2 M's in this group. It's called 2MM. One is the inserted mirror plane, and the other one represents at least one generated mirror plane. Now let's look at these 2 multiplication tables. Are these multiplication tables isomorphic? You look at them, tell me, yes or no. Well, I hope you said no, because if you look at the one on the left, which is the multiplication table for point group 4, we see that down the main diagonal we have 1, 1, and then we have 2, 2, whereas on the one on the right, which is 2MM, we have 1, 1, 1, 1. We have the identity all the way down the diagonal. So you could never get these 2 to be isomorphic with that condition. So you can tell right away. Here's our appendix, and again you can see we have 4 elements, and they are indicated by the identity and the twofold, and then the third one is the mirror, and the fourth one is the mirror perpendicular to it. And here we have the generators. The generators this time refer to the identity, the twofold, and the M sub Y. The rectangular system, we'll tell you about that later. Now we have point group 3, and you can see here's our molecule. It's 1,3,5 triamino 2,4,6 trinitrobenzene. It's not a chemistry course, so you don't really have to learn that, but I think you can see from the figure that we have the threefold is obeyed. And now we can put in the threefold and its mirror planes here, and let's do some analytical expressions for this. Now what's different here is the axes which we've chosen for our for the point group 3M are 120 degrees apart. So when we construct the analytical expression for the mirror, they're different. The analytical expression is different from that constructed if you have different axes. So here we have this mirror along XX takes 1, 0 into 0, 1 and 0, 1 into 1, 0. So using the method we developed earlier, we can add that together and we see we have XY going into YX. What's the matrix representing this particular mirror? You go ahead and do it. Yes, it's 0, 1, 1, 0, and you can see that that determinant is -1. And another thing is, if you take the MX mirror and you have a threefold here, you generate a Y and an MY and an MX. Notice if you, let's look here with the, before we do that, here's the product, and here is our point stereographic projection, and here is the identity with the threefold, and then if we put in a mirror along the y-axis, we have the red going to the blue, the red going to the blue, and the red going to the blue, and here are our two matrix generators. Now this multiplication table is not symmetric, and you can tell because here these two green ones are highlighted, are not central, are different, as are all the rest of the yellow ones. Now let's have a little review. If we want to multiply two functions, given function f of x and g of x, if we want to multiply them, f times g, what we really need to do is we need to evaluate the function g at x and then evaluate the f at the g of x. So we apply that when we work with 3M. So let's look at the multiplication of mxx times 3 plus. So this is the function 3 plus. So here we start out with our blue ball, and we rotate it counterclockwise by 120 degrees, and we come here, and then we want to reflect it across the mxx mirror. So there it goes. And if we wanted to go directly from the blue to the green, we could have just traveled across the mx. So that's what this product is all about. mxx times 3 plus gives me the mx. Now let's do it the other way, and we see if we take our blue spot and we go we mirror across mxx, so we come over here to this yellow, and then if we do a counterclockwise rotation, we come up to the green. And if you want to go from the blue to the green, you see that we're really mirroring across the my, so that's equal to my. So 3 plus times mxx equals my. Now, the non-commutative group does not have a symmetric multiplication table, and there are our 6 symmetry operations. And now there's another thing that we need to look at. The way we have set up our axes at 120 degrees apart, we can put the mirror down the short axis, or we could put the mirror down the long axis. And that has the effect of rotating our figure. So we take this clover, 3-leaf clover, and if we have the mirror down the short axis, it's going to look like this. On the other hand, if we put the mirror down the long axis, so this axis is just translated over here, this is and so we get a rotated figure. Now, as far as the point groups go, their axes are, it's sort of arbitrary whether you put you put it in one way or the other, simply rotating the whole figure. It really this does not matter. So we can develop analytical expressions for the two different positions of the mirror. We actually give them two different names, 3-1M and 3M1. I don't require you to know that, but I do require you to know that there are two different operations. This occurs in point groups where the axes are 120 degrees apart. Now, just another, you can just sort of see how we're labeling these. These are the MXX, and we got the MY and the MX from the threefold. Here, if we put the MXX bar, and remember this, if we this is the X bar direction, so it's you're going to go plus X and minus Y for a crystallographic direction in the 1-1 bar. Now, if you rotate the 1-1 bar around and produce two more axes, you can see, for example, this axis, you go in X, you go 1, 2 in X, and 1 in Y. So that this direction is the 2-1 direction. And so we have these two different ways of looking at them and these two different ways of labeling the mirror planes. So here are the matrices, and here are the two versions of the 3-1M and 3M1. In this particular one, we have the mirror along the x-axis and the y-axis. Here we have the mirror plane is not along. This one here is perpendicular to the y-axis, and you can see that you get different projection. This looks a little bit different. If you start out the identity and you operate the threefold on that, that's the same in both of these. But in the bottom one, we have a vertical mirror plane, so we come across like this, and we come across this red to blue and red to blue. However, if we have a horizontal mirror plane, then we have our red to blue, our red to blue, and our red to blue. And so, in effect, we have a wheel here, and the wheel is slightly rotated between these two terms. And I've, in the appendix, I circle or outline the two representations of the 3M point group by enclosing them in a red box so as to keep everything a little bit straight. Now let's move on to 4MM. We have xenon tetrafluoride as our example, and here's a figure, and I'm not going to go too much into detail. Here's the M4 matrix, which you can easily derive. You know how to do that. And another M, Y, and now we can set up 4 plus times MY, and we get a new MXX, and now we can, and here's the figure, and now we put in the point stereographic projection, much as we did before, and finally we have the symbol stereographic projection. Now what you want to notice here is if you put in, say, this mirror and you operate 90 degrees on it, you're going to get this mirror. You operate 90 degrees on that mirror and you come back to what you got. So you only have two mirrors that are generated by the symbol, and then there are two more that are generated as you get closure. So that's why we have the MM, the two M's representing the two types of symbols of mirrors. And finally we have the 6mm, and here is a figure. If you omit the central part, you'll see this is a church. It's a St. Mary's Church in Blacksburg, and if you omit the central figure, you'll see you have 6 mm symmetry, and here's what the point group looks like, and here's what the symbol looks like. And you'll see when you write this out that you use all the projections of both orientations of the 3M and 3M1, and you'll so you actually have that all ready to go for yourself. And there's your benzene molecule, which exhibits 6 mm symmetry. Now let's identify it. So if you have a pattern and you want to identify the point group of that pattern, this is a surefire way to do it if it's crystallographic. And you look first of all for the highest crystallographic axis, which will be a 6-fold, and then you look for, does it have a mirror? If it's yes, then it's 6 mm, and if it doesn't, then it's 6, and so forth. 6, 4, 3, and 2. And if it has a mirror, you can either have 2 mm or 2. And finally, if it has no 2-fold and no other rotations, then you simply look for a mirror, and it's either M or 1. This is a complete list of all 10 point groups. Here's a couple of examples, which I will give you in quizzes and on tests. Here is a house. Now, you look at that house, and do you see 6-fold? Hope not. 4-fold, 3-fold, 2-fold, 1-fold, no. Mirror, yes. And here we have the mirror. So the symmetry of this object is M. Finally, we come over here and we can look at this tile, and we see we have 4 corners here, and each has a little symbol in it. So remember, the 4-fold has to be universal. Every part of it has to obey the 4-fold. So the highest, we don't have a 6, we don't have a we have a 4, so it's going to be 4. Do we have any mirrors? Well, here's the 4-fold. Well, if you come down here and you look right down here, you'll see a mirror. So we have 1 mirror, 2 mirrors, 3 and 4, so it's 4 mm. Now, what about this one down on the lower left? Is it a 6-fold, 4-fold? Yes, it's a 3-fold. And do we have a mirror? Yes, we do. And here are the mirrors. And finally, what about this last figure? What do we see? Well, 6, 4, 3, yes. And is any mirror there? No. Those little wiggles break the mirror. Here's a pin, a Zuni pin, and it has an inner design which is 7-fold and an outer design which is 20-fold. Those two numbers do not have anything in common except the 1 for the low in terms of a multiplier, lowest common multiplier. And so the only thing possible now is the mirror, and we'll assume that mirror, it's meant to be a mirror plane. And finally, you do these. This is an example of a non-crystallographic group. You can see it's a 5-fold. Has it got a mirror? Yes, so it's 5M. Here we have, you come down and the only thing you've got here is this mirror plane, and so it's M, and then this one is 3M. Here's anthracene, and what is that? Yes, you see 2 mirrors and a 2-fold, so that's 2mm, and this one has got 6, 5, 6, 4, 3, 2, 1, and it's got a mirror plane. So there's the mirror going through the sulfur. And finally, here we have another 2mm. You study these so until you're absolutely sure how to do them. This is, you can see the 3-fold there, so that's 3M. And finally, what is that? Yes, it's not a trick, it's 1. That's all, folks. I think I need a drink of water. I bet you do, too. Bye.